All right, welcome to my presentation on my term paper, which is called The Architecture of Microseconds. It's an analysis of ultra low latency network technologies and high frequency trading. So, just going to start off with the introduction. This paper is about analyzing how HFT networks work, which is high frequency trading. One of the reasons why I chose to do my topic on this exam is because I work in fintech. I'm a DevOps engineer in fintech. So right now I work on the bank side of doing bank transactions, but I do plan in the future to migrate to high frequency trading. And I thought this would be a good thought exercise to compare how traditional enterprise model that we see in class and that we learn, and how is kind of flipped on its head in the HFT or high frequency trading world. So, starting with this introduction here, I have included a table here that explains the topology and the goals of a traditional network model, such as how it's a hierarchical structure layer with the core layer, the distribution layer, and the access layer. The goals about and the strategies it has to get high availability and redundancy, and then the benefit that it has of providing massive bandwidth using such technology such as WDM. So that is that table. And then here I have a diagram that kind of gives a high level overview along with a summary of how a traditional enterprise network model works, which is what we use all day for our homes and for our businesses and for general computing of that network layer. And then I transition into talking about high frequency trading, and I start this off with speaking about the order book. The order book is very important in high frequency trading. It is the root requirement of how the network is built and why it's built in this way. I actually found this research on this very exciting and a very fun topic to research because I learned more about how trading works and just in financial markets in general. So with that said, I have some preliminary information about what an order book is, pretty much the sides of it of, the functions that it can do, the data that it's trying to transfer, and then what exchanges provide. And this is important because at a high level, an exchange provides a market data to these trading servers for these high frequency trading servers, and they have to sit very near this exchange so that they don't get a lot of latency. And the reason that happens is because high frequency trading firms, they want to minimize latency because one of their strategies to make money is to buy prices at a different price than what the market is. So if a stock is traded for $99, but someone's asking $100 for them, then the high frequency trading firm will buy at $99 and sell to $100. And the reason why this is also important is because most of these HFT firms, they provide liquidity in the market, meaning that they provide when there are no buyers or sellers for stocks and things like that, and a person wants to sell, they provide liquidity. And as I mentioned earlier, I work at the Federal Reserve. I've worked in fintech, and what we do is that we provide liquidity to banks and HFT firms and things of the like. So this is why I found this to be very interesting paper to work on. So here I also included a table talking about the characteristics of a traditional HFT network architecture. They use an ultra flat network topology. It's the first time I actually heard of this, but basically it's super simple. It's a collapsed spine leaf where you have like a one tier or two tier model. This kind of replaces the core distribution access layer that you would see in like traditional CDNs or the traditional enterprise network model. I thought that was pretty interesting, but it makes sense because you only want to be 1-2 hops away from the exchange engine and then the trading application. And I live in Chicago, and we have a bunch of HFT firms around us, and we also have a bunch of fintech banks around us. So this is very equivalent because we have a data center where all the HFTs are stored at with CME, which is 30 miles away in Aurora from the city. And everyone has all the HFT firms have their servers there, and they have their trading applications right there next to the exchange data, and that's how they're getting all that data there. So I'll talk about some more things such as co-location, which I just mentioned, the L1 matrix switching. This is basically how they HFT firms and data centers, they use L1 switches. They don't have the deep layers that a traditional CDN or data center will have with the L2 and L3 switches. Where, and by L2 and L3, I mean access layer and distribution layer. Some of the characteristics of an HFT network is high availability and determinism. So one thing that I thought was very interesting was that they do A/B feed arbitration, which basically means that they have two parallel lines running between their devices and their network, because they can't wait for a failover because they have to transmit market data in a very consistent and quick manner, just the way that the stock market and the trading market works. And so basically what happens is that instead of waiting for a failover or like the automatic protection switching where it detects that like a node is down and then it switches over, what happens is that HFT networks actually send data at the same time directly to that device or that server, and then whichever data gets there first or whichever line gets the data first, that device actually takes it in and then it constructs it that way. It does not wait for all the data to get somewhere and then reconstructs it and then continues to send it. It's sending the data consistently at all times through parallel lines. So I thought that was pretty interesting. And then I would say the next thing that I thought was important to note was the microwave and the millimeter wave technology that these data centers use to send data. So they use microwave technology to do like a lot of long haul data. So for example, from like New York to Chicago, HFT firms they use like line of sight wireless towers to because signals can be sent through the air faster than they can be sent through the wire. But however, there's a caveat with that because that you don't have a lot of bandwidth with sending data through the air, meaning that there's only so much data that you can have. So HFTs usually try to send more important and critical data through the air, and then like the more generic market data or things that are more complex that take up more bandwidth is getting sent over fiber. So I thought that was very interesting how they use a hybrid approach for that. I do talk in this paper about the hardware a lot. I do have to talk about the CPU, like such as core pinning. I've talked about like FPGAs, and I'll talk about how they use like bypass technologies, and I also mentioned things such as some protocols they use at the application layer so that they can encode their data quickly at a more hardware level instead of waiting for it to be kind of deconstructed and then reconstructed again because that increased latency. So I do talk about a bit of hardware in this, but I would say the takeaway of that is though that it all relates to the network. I mean, the requirements for HFT network again comes back to that order book and how market data is. And you think about the stock market, right? It's on from like 8 p.m. to 4 p.m. 8 a.m. to 4 p.m. And then in some cases it's even on in 24 hours in some instances. And to be able to send that data is very important at all times. So you have to have that consistency. You have to have no latency or minimize latency because that is the key to supporting those markets so that people can make decisions and get that data to trade. So that's where the CPU and the hardware aspects come in. But it is directly related to how the data packets are sent through the network and where they're going, the destination. So that's one thing I would like to know. I talked about bypass, core pinning, spoke about that. Spoke about fault tolerance. So yeah, I pretty much enjoyed this term paper. I believe I gave a good overview of all topics that I will be speaking about in this paper. It does get a little technical, like I said. Oh, here we go. One thing to mention is the design decisions, usage patterns, and trade-offs. So I'll talk about a little bit about microwave and fiber optic routing earlier. One thing is also interesting that I found when researching this is cut-through switching. Cut-through switching is where essentially you have the switches, like I said, not do like the checks of waiting for handshakes, not having the OS kernel involved, where basically you're just constantly sending that data through and you're bypassing the kernel. One thing that I did find that was interesting was that if you are doing cut through switching, and then you have a sudden spike in data that is getting sent through the network, you can get something called like latency spikes or like microbursts, where basically the information through the wire, instead of being at a consistent pace, it starts going like that, or it might go faster, and that can cause, and those changing pulses can cause a buffer overflow onto the server, and that can lead to packet drops or like queuing delays, known as buffering. But one thing that is nice though is that now modern switches now, they use dynamic buffering allocation. So I think like Cisco and another brand, I think it's Arista, they have these new devices to where they have chips on them that dynamically do buffer allocation, instead of just assigning a certain amount of memory per each port, which is, I thought, was pretty interesting. And that is all for me. The final notes I would say is that, in conclusion, um, the fundamentals of learning about traditional network architecture gave me the ability to understand how HFT firms and networks work, and I found that to be very insightful, because that's like what my career aspirations are going forward once I graduate soon. So I hope you enjoy reading this paper as much as I did researching it and writing it. So thank you.